Okay, so good morning. So let's start slowly. It's early in the morning and it gets earlier every day. At least that's how it feels like. So let me make use of this other blackboard to give you a brief recap where we are so that we sort of remember what we've been doing. So what we've been looking at is the conformal symmetry. And in general dimension, that's generated by translations, rotations, dilatations, and special conformal transformation. And if you specialize this to 2D, that gives you the Möbius group. By the way, I should say that this generates, I didn't quite say this right yesterday, this generates SOD minus 1, 1 in Euclidean space. I said SOD plus 1, 1 in Euclidean space. I said SOD plus 2. That isn't quite right. It's a different real form for the Euclidean space. So this is in general dimensions. And in 2 dimensions, that becomes SO2, 1, which is, up to different real forms, SO3 or SU2, which is really SL2C. So, you have to complexify and so on, but the Möbius group is SL2C. These are the fractional linear transformations of the sphere. So these are the global conformal transformations. But then in 2 dimensions, you also have the infinitesimal local conformal transformations that are of the form Z goes to Z plus epsilon Z to the n plus 1. And we denoted the generator that corresponds to that transformation, Ln. And then we saw that simply from the way it acts on the space, that they satisfy the Witt algebra. So they satisfy the Witt algebra, Lm, Ln is equal to m minus n times Lm plus n. And then, as we saw in the examples of the quantum theories, one may expect from normal ordering some central extension to appear, and we classified what the central extension can be, and we saw the central extension can always be brought into that form. There's only a 1 parameter freedom of possible central extensions, and up to redefining the generators, you can always bring it into this form. And that's the canonical form in which you bring this algebra. Then you call it a Virasoro algebra. And this parameter you call the central charge or the conformal anomaly, and that will characterize different theories. And then we looked at 2 examples. The 2 examples we looked at is the free boson theory, for which the field d phi had the form, it had a mode expansion of the form an z to the minus n minus 1. And it realized a conformal, the stress energy tensor in that case was equal to Lm is equal to the sum over L, Am minus L, Al. And that gives rise to a Virasoro algebra with central charge C equals to 1. Yeah, sorry, this blackboard is a bit small, and there is this in the, so I can't lift it up. So this is, anyway, this is just a recap of what we've done. And then the other example we looked at is the free fermion theory. There the field psi of Z has a mode expansion of the form sum over R, BR, Z to the minus R minus a half. And there is a similar expression for the stress energy tensor, and it gives rise to a Virasoro algebra of central charge a half. So that's what we've done so far. So now we want to discuss one further example. So you think in some sense that's all the interesting examples, but actually it is interesting to look at the example of n free fermions for reasons. So the third example. So we do one more example, namely that, because that introduces yet another new concept that will prove important later on. And then we'll sort of we'll calculate the amplitudes of these fields to get a sense of what the correlation functions look like. And once we've acquired that information, we feel we are in a position to sort of abstract the description and give a more formal description of conformal field theory, into which all of these examples will naturally fall. But that is much more general, and then I'll explain to you from there what's the powerful techniques to construct, discuss, and analyze conformal field theory. So we work up from examples to get a sense for the structure, and then we try to formulate it more abstractly and learn general lessons. So the third example is simply n free fermions. And you may say, well, that's pretty boring because, okay, so I have this psi, so now the psi becomes Actually, there's a factor of 1 over square root of 2, but who cares? I mean, it doesn't matter. So so now we have n fermions. So let's call the fermion fields Bi of Z. So strictly speaking, there's a factor of 1 over square root of 2, and I don't want to deal with this stupid factor of 1 over square root of 2. So I'll define the fields Bi of Z, and they have a mode expansion like the guys above. So each of them has this mode expansion, and then each of them, these modes satisfy the obvious anti-commutation relations. So we worked out the commutation relations for these guys. They should be delta R comma minus S, and now you have n copies, and each copy should only talk to itself. The different copies live in different universes, and they obviously don't talk to each other. And then you can write on the stress tensor. And the stress tensor will simply be the sum from I equals to 1 to n of the individual stress tensors LIN. And the LINs will be given by a formula which I didn't have space to write down over there, which is the sum over R times BIN minus R BIR. I should have, so these are normal ordered here. And likewise, you have to normal order the fermions here. And each of them has central charge 1/2, and if you add n 1/2s together, the central charge of the whole thing will be n over 2. So that's not a big surprise, right? I mean, you just have n copies of a theory, each of which has central charge 1/2. You add together the Virasoro algebras, they mutually commute, and therefore the central charges just add. There's nothing particularly funny happening here. Now, why is this example interesting? Well, this example is interesting because you can actually give it a little bit more structure. So suppose we have a Lie algebra. So suppose G is a finite dimensional compact Lie algebra of dimension D. So it's a finite dimensional, simple, compact, whatever you want, all the good things in the world. So you should think SU2 or SUN or SON or E8, if that's your inclination, or G2, doesn't matter. Any of the ones you can think of, compact Lie algebra. So what is a Lie algebra? So it has dimension D. So the dimension is equal to D. So that means it has generators TA, where A runs from 1 up to D. So, I mean, it's a D-dimensional vector space, so you have a basis vectors T1 up to DT. And the fact that it's a Lie algebra means there's a Lie bracket, and the Lie bracket takes the form TA, TB is equal to, and now I'm using physicist notation. So physicist likes to put a factor of I here. I'll explain in a second why this is natural for a physicist. So what this is just FABC are called the structure constants. These are numbers. These are real numbers. And the sum over C is implicit. So you sum over C. So what this tells you, the commutator of TA and TB is a linear combination of the generator. So it's another element of the Lie algebra, another element of this vector space. So I can write it as a linear combination of the basis vectors. And the elements that appear in this description are called the structure constants of the Lie algebra. Now, physicists like to put a factor of I here because they want to think of the TA as being Hermitian operators. Because you see, if TA is Hermitian, then TA dagger is TA, but TA, the dagger of a bracket is minus the bracket if they are Hermitian. So the dagger of a bracket is anti-Hermitian, and therefore, if this is Hermitian, you have to multiply it with a factor of I, so that it's anti-Hermitian. So in this convention, the T can be Hermitian. If you don't put the factor of I, the T would have to be anti-Hermitian. And that's a little bit, anyway, physicists like to put a factor of I there. Okay, so suppose we have some finite dimensional simple compact Lie algebra of this form, and this dimension D is not equal to n, but what we assume is that this Lie algebra has an m-dimensional representation. So suppose a G has an m-dimensional representation. So what's a representation? Well, a representation, what's an m-dimensional representation? Well, an m-dimensional representation is an assignment from TA to I times MA, and MA is a matrix. So MA is a n times n matrix. Right? So what's a representation? A representation is for each abstract generator of the Lie algebra, you choose an n by n matrix so that the commutators are respected by the matrix. So what this means is that MA, so if I calculate MAAB, MB, so remember, these are now n by n matrices. So what I mean by that is I multiply the two n by n matrices, then I multiply the matrices the opposite order, I subtract them from one another, and then that should be equal to FABC times MC. That's what you call a representation of the Lie algebra. It's an assignment. I mean, it means that the TAs act on an n-dimensional vector space, and the way they act is described by this matrix M. And in order to respect the structure, i.e. the Lie bracket, these matrices have to satisfy this commutation relation. That's what you call a representation of the Lie algebra. So for example, for SU2, SU2 has a representation of, an irreducible representation of any dimension, right? The spin J representation has dimension 2J plus 1. J is either 0 or half or 1 or 2. So you get a 1-dimensional, 2-dimensional, 3-dimensional, 4-dimensional, and so on. For SUN, it's a bit more complicated. SUN has an n-dimensional representation. Then it has a half into n times n minus 1, a half into n times n plus 1, and so on. But there's a whole zoo of irreducible representations of finite-dimensional Lie algebras, and we assume that we have a finite-dimensional Lie algebra that possesses an n-dimensional representation. Now, once we've got that, there is something natural we can do. We can, so this is some abstract Lie algebra stuff, and now somehow we want to import this into our free fermion theory, and the way we import this is that we say, then we can also define, we can define a representation of G, then there exists a representation of G acting in our Fock space. So I should have said, so these theories generate the Fock space. So what does this Fock space look like? So remember, the Fock space is generated by the BI1 minus R1 up to BIL minus RL acting on the ground state, and the ground state is characterized by the fact that this is 0 if R is greater than 0, and the negative modes create some Fock space. So this is the Fock space of this free fermion theory. If I only have one species of fermion, then obviously there is no upper index. If I have different species of fermion, I can apply whatever fermion I want. I can bring them into some canonical order, but it doesn't matter. So there is a Fock space of this. And what I'm claiming is that this Fock space actually carries a representation of the Lie algebra G. And the generators are defined by saying TA. So I have to say, who does TA get mapped to? And TA gets mapped to JA0. And JA0 I define to be I times the sum over R. BI, BJ, and take the R greater than 0 term. BJ minus R, MAJK, and BKR. Right, so the M's are n by n matrices. So if I want to write the m by a matrices, I write them as ij. So the ij indices run from 1 to n. So these are so M carries 3 labels. One is saying which generator of the Lie algebra it corresponds to, and I and J are the matrix elements of the n by n matrix. Right, an n by n matrix has a row column, a row parameter, and a column parameter, and that's what I and J is. So this product is Mij Mbjk minus Mbij Majk. So here I take the matrix element, and what I do is I contract the right index with bkr on the right, and the left index with the bj minus r on the left. And I claim that this furnishes a representation of the Lie algebra acting on this Fock space. Is it clear what I'm claiming? And it's not that hard to see that this works, right? So what do I have to calculate? Well, I have to check what's the commutator of JAB and JB0. So first of all, I should say, so you may be worried about normal ordering. Well, here I've sort of taken care of this by writing only r greater than 0. But you see, these m's, without loss of generality, if this is a compact simple Lie algebra, these m's will be antisymmetric. And therefore, they will and the only ambiguity in the ordering will come from the terms when j is equal to k. But if this matrix is antisymmetric, such a term can never arise. So I should have said these are antisymmetric matrices. So these matrices satisfy Mij is equal to minus Maji. That's because once you've put in this factor of I, they should be anti-Hermitian, and therefore they are antisymmetric if they are real. Okay, so this is the generator, and now we simply have to check that this satisfies the correct algebra. And so what I claim is that this satisfies I times FABC JC0, and it's sort of, okay, it's maybe I can try to write it out. So we get a factor of I from both of them, so we get a minus sign, and then we have a sum over R and S. And then we have a Bj minus R Ma Jk Bkr, and then I have to take the commutator of this with Bl minus S MBL M BMS. Right? So this is what we have to calculate. And now you can see what's going to happen. Because R is bigger than S, the only terms that contribute is this term, right? I mean, the commutator, the anti-commutator is such that the mode numbers have to add up to 0. R and S are both positive, so the only terms that can be non-trivial is if you have an R with a minus S, or an S with a minus R. And then, so this one will lead to K and L getting contracted. So this will lead to the matrix product MAJKMBKM, because the L and K get contracted. And then if you do it the other way around, the other term you can get is this guy. And if you calculate this guy, then you just contract the J and the M index. So that's multiplying the matrices in the opposite order. And then you use the fact that the M's satisfy this identity, and then you get out this formula. So that's how you see that this operator actually leads to a representation of the Lie algebra on this Fock space. Okay, so, okay, maybe it's not surprising. You have n of them somehow. So what this means is somehow these n fermions sit in the m-dimensional representation, in this m representation, and you can sort of rotate them, and as a consequence, the Fock space inherits this action of the Lie algebra. But if you look at this formula, you see, and in fact, I've already indicated it here. I've written a 0 here, and you see, this looks very much like these sorts of formulas. Like these sorts of formulas, right? I mean, you contract somehow mode numbers in such a way that they add up to some mode number on the left. And here, because I'm taking R and minus R, they will add up to the mode number of 0. So this has the property that if you contract it if you calculate a commutator of JA0 with the field, with psi j of z, or what I guess I call it bj of z here. So this field up there, then that is just equal to minus I times m a jk psi k of z. Sorry, bk of z. So this just follows from the fact, again, if you think about it, bj of z is just the sum over r, bjr, z to the minus r minus a half. So when you calculate this commutator, you see it's only this term that can contract with this term. So it's the second term that can contract, and therefore you get the minus sign because you want to contract the first term, and since m is antisymmetric, you just turn it around. So this is the way this Lie algebra acts on these individual fermion fields. And what it just says is that the fermion fields sit in this n-dimensional representation of the Lie algebra. But now, as I was starting to explain, given that you've written down the JA zeros, and given the form they take, it's very natural to generalize it to something that wants to have an affine label, wants to have an n label. So a natural generalization is to define JAN. And JAN we simply define by the analog of that formula. So we take this formula and now we write it in maybe normal ordered form. We write it as I over 2. So here we had a factor of I because we picked the specific normal ordering. Now we are going to sum over all integers. So every term will appear twice. So we better write an I over 2. And then we write a sum over all integers. So we are not just restricting to the positive integers. And then we simply write bj minus r majk bk n minus r, where n is an integer. You see, n has to be an integer because the modes of the fermions are all half-integer moded. So if r is half-integer moded, then n minus r will be half-integer moded, provided that n is an integer. So I have to pick n to be an integer so that I only encounter half-integer moded modes. So this is sort of the Ln type generalization of this guy. And you can ask, what sort of Lie algebra will they satisfy? And it's not that difficult to see what sort of Lie algebra they will satisfy, because, I mean, actually, maybe I'll try to do this computation, although I'm worried I'll make a mess of it. Okay, let's try this. So let's take JAN with BJR. That we should be able to get even on a Friday morning. Yes? Oops, you're right. So it should be, yeah, it must be, which way, it doesn't matter, but I should probably put this here, yeah. So, yeah, absolutely right. The mode number should sum up to n. So it's minus r plus n plus r gives you n. Yes. So this is the generalization here, where instead of this 0, now I have n plus r here. And n is not equal to 0 anymore.
Do we have to do a normal ordering?
A very good question. We don't, because you see, this matrix is antisymmetric. And the only non-trivial commutator arises if j is equal to k, but a term where j is equal to k doesn't arise because this matrix is antisymmetric. So I have an antisymmetric matrix representation because I've chosen my factors of I appropriately, so this matrix is antisymmetric. And then, since it's antisymmetric, normal ordering doesn't play a role. I could normal order it, but it wouldn't make a difference because the terms where it would make a difference are all 0. Okay, so let's try to work it out, at least this once. Okay, so what is this? So if we calculate this, you see you get I over 2, and now we get the sum over r, and then we get the commutator of bj minus r majk bk of n plus r, and let's call this s, bj of s. So if we calculate this, what do we get? We get one term from here. This term will be, oops, it's also bad to call this j. So, okay, let's not call this j, let's call this L. I mean, you know, dummy indices should never be confused with exterior indices. So if this external index is a j, I can't use as a dummy index j, otherwise I don't know what I'm doing. So then I have the fundamental freedom of a theoretical physicist is to relabel the dummy indices. It's about the only freedom you have in life, but that you do, and you have to use it liberally whenever you have a chance. So this is the relabeled dummy index, and now I can work out this commutator. So there's a term coming from this guy. So what do I get if I take this commutator? Okay, so for this commutator, k will be equal to j, so this index will become a j. And then n plus r will be equal to n plus r plus s is equal to 0. So if I think of this in terms of r, this means r is going to be equal to minus n minus s. So the term that will survive is bl n plus s times MA Lj. That's what survives from the first contraction, right? But now remember, these are anti-commutators. So once I've moved it past the first one, I get minus the term. So the other term is minus I over 2 when I contract this guy with this guy. When I contract this guy with this guy, then obviously R has to be equal to S, because NL has to be equal to J. So what's the term I get then? So then the term that survives is a BK, and then it's an N plus S, right? Because R is equal to S. And then the matrix that multiplies it is MA, and now this index L has become a J. It's MAJK, right? And now if you look at this, you see these are both the same term, because this matrix is antisymmetric. So here, the first index is being kept fixed, and the second index is summed over. Here, the first index is summed over, and the second index is being kept fixed. So I swip them around. That compensates for the opposite minus sign, and then it depends just in which way I want to write it. So this is equal to minus I times MAJK BK N plus R. So that's how the M's act on the B's, right? Okay. That's not that difficult. And now we can work out what the J's do with the J's, right? So that's also not that difficult. Let's be brave and have a go. Okay, so let's try. So now we can calculate what's JAM on JBN. Well, the idea is the first JAM I'm going to leave standing because I have already calculated how the JANs act on the B's, and I'm going to write out the second one in terms of this, this sum. So I write this as I over 2 times the sum over R. And then I write this as JAM with BJ minus R times MB, this is the B, MBJK, and then BK N plus R. Right? This is what I have to do. And now I get the term where I contract this guy, and now I can use this formula twice. So what am I going to get? I get an I over 2. Then from this contraction, I get a factor of minus I. Then the sum over R now keeps standing. And I get a term that looks like M A JL BL M minus R MBJK BK times N plus R. Right, this is the first term I get. And then the second term I get is plus the sum over R. So this was this guy, and then I have this guy, right? So this is a commutator, so once it's gone through, it's a plus sign here, because this is bosonic, so when it goes through, it's a commutator, so it doesn't pick up a minus sign. And what's left behind is BJ minus R, MBJK, and now I'm going to pick up this guy. So this is again a factor of minus I times, and now I'm going to get MAK KL BL M plus M plus R. Right? Okay, and now you sort of, okay, so now we can try to work this out in detail, but actually that's getting very, very difficult now for reasons that I'm about to explain to you. But what I want to highlight for you is that, you see, this basically looks like, this is the matrix product of MB with MA, right? Because you contract the K index. So this expression is just MB, MA, the matrix JL, right? That's what this means, because I contract over K. Whereas this one isn't quite, it's almost the opposite, but I have to put in I have to flip them around. So this one is equal to minus, this is equal to minus MA, MB with the indices LK. Right, and I should, so let's relabel this as K. Oops, I shouldn't have done that. Oh, that's bad. So let's relabel this as L and this as K. So then this is the JK label. And then relabel this as, let's change what we call L and J. So let's call this L and this J. Then this is the matrix JK. So what you see, you're going to get the commutator of MA, MB, the JK's matrix element, decorated between BJ and BK. So once the dust has settled, what you find is that this is going to be equal to I times FABC times the generator JC M plus N. Right? Because you see that, so for example, this term, now the mode numbers add up to M plus N plus N, both here and here. Right? So you get this term, but you get in general a central term as well. And the central term is actually quite tricky to calculate. So you see this term is already in good shape, but here you have to relabel, and then depending on these matrices, there is also the possibility that now you pick up a central term, and there is actually a central term, and the structure of the central term you can essentially determine by the same arguments that allowed us to determine that. You can simply ask, what's the most general form of the central term I can write down that's compatible with the Lie algebra relations? So this is, again, in some sense, determining the cohomology of this Lie algebra, and what you find is that this term, the term that can appear, is of the form K times M times delta AB times delta M minus N. You know that that's the only thing you can find, but, or rather, you can always bring it into that form, and the argument is an analog of the argument that allows you to do that. So, for example, that's a good exercise for you. It's not an entirely trivial exercise. Actually, I'll prepare for you an exercise that guides you through this problem. It's a little bit, I mean, if you are just left to your own devices, you'll probably struggle a little bit, but if one talks you through it and tells you the intermediate steps, it's actually not that difficult, and it's a variant of the argument that lets you prove that the Virasoro algebra can be brought into this form. You can show that this algebra can be brought always into this form. This is the only central term that can possibly arise once you've chosen your generators, brought it into canonical form. So this is called an affine Kac-Moody algebra. And and in fact, in the case of the free fermion theory, we can calculate what this K parameter is. This is a bit of a tedious calculation, and I'm not sure it's really, I mean, I can go through it, but I think you've seen probably enough of calculations of that kind. So, I mean, if you want, we can do it in detail, but my sense is you would rather, it's maybe more instructive for me to tell you other stuff than doing in front of you lots of calculations and getting them more or less right. So I'll just tell you what the answer is, and I hope to convince you that by the same sort of arguments that I spelled out in great detail yesterday, you can do this analogous computation. It's just technical. I mean, there's nothing, I'll say something what this means in a second, but there's nothing particularly deep about it. So what you find for the case of the free fermion is that the central term is determined by the trace of the so k times delta AB for the case of the fermion turns out to be a half into MAJK MBJK, which is the same as minus a half into the trace of MA and B. So what this is related to is the value of the quadratic Casimir of the Lie algebra G evaluated in the representation that you picked, the representation given by the labels M. So this is, you see, this is diagonal in delta AB, so you may as well think of this as being delta AB. If you sum over TA, that's the quadratic Casimir, that's the generator. So this is not a generator of the Lie algebra because it's bilinear in the Lie algebra generators, but it's the quadratic Casimir that has the property that it commutes with all Lie algebra generators. So this is, in quantum mechanics, that's the angular momentum squared operator. That L squared commutes with the Lie algebra, with the rotation generators. And there's an analog of that for any Lie algebra. That's called the quadratic Casimir. It's called TA. And what this tells you is TA will be a number in each irreducible representation. And when you take its trace, it's basically just this number times the dimension of the representation. So this level K is related to the quadratic Casimir in the representation M together with it. Well, the dimension falls out because when you do the sum, well, anyway, so it's related to the quadratic Casimir and the dimension of the representation, the dimension of the Lie algebra, but it's some property that depends on exactly which M you pick and which G you pick. There isn't an answer that I can just give you. It's implicitly determined by that, but it's not that I can say it's two. It depends, right? It depends on which Lie algebra you pick and which representation you pick. And you can sort of see how this comes about. You see, when you contract, so when you renormal order this, you see there are terms so suppose you pick M and M to be positive and N to be negative. You see the central term only appears when N is positive or negative. Then you have to be careful, but you have to reorder one of these terms. And when you reorder one of these terms, you're going to pick up a term that is a JK contracted. So then you are contracted L with L and J with J. So you get something that will be of that form, right? Because that comes from the anticommutator of this guy with this guy. Obviously, this anticommutator is only non-zero if M minus R plus N plus R is equal to 0, i.e. if M plus N is equal to 0. So it must be proportional to that sort of term, just for the Virasoro algebra, and it'll be proportional to that bit. And if you do it carefully, you find it's exactly of this form where the parameter K is given by this formula. Okay, so that's an affine Kac-Moody algebra. So what is an affine Kac-Moody algebra? So we know what the Virasoro algebra is. The Virasoro algebra is the algebra of infinitesimal conformal transformations. So you can ask, what's the affine Kac-Moody algebra? The affine Kac-Moody algebra is the Lie algebra of the loop group. So the affine Kac-Moody algebra is the Lie algebra of the loop group Okay, so that probably contains absolutely zero information for you because you probably don't know what the loop group is. So let me tell you what the loop group is. Well, suppose you have a circle. So suppose you consider the maps from the circle into the group, right? So each f is a function from the circle into the group. And let's parameterize the circle by a parameter theta. I can write f of theta as a function of no, I'm not sure I really want to do this. Not yet, anyway. So these are the maps from the circle into the group. And you see, they form a group. Because if I have a function f and I have a function g, I can declare what f times g is. And f times g evaluated on theta is simply f of theta times g of theta. Right? F of theta for every value of theta is an element of the group. G of theta for any element theta is an element of the group. I know how to multiply group elements. So this is another element of the group. So given a function f and given a function g, there is a function f times g, which is the pointwise multiplication of the function f times the function g. And that defines for you another element of the loop group, namely another map from the circle into the loop group. Now you should ask, what is the Lie algebra of that? Now think about it. So the Lie algebra is the tangent space to the identity, right? That's what you always hear. So you should think about maps that go to the identity element of the group, and you sort of perturb around the identity element of the group. Now, what's the identity element of this group? Well, the identity element of this group is the map E of, well, let's call it F0 of theta. That simply maps all elements theta to the identity in the group. That is surely the identity element of the loop group, because if you multiply this function with any function, then you just multiply the function always with the identity, so it stays the same function. So that's the identity element of the loop group. It's the most trivial loop. It's the loop that's not a loop. It's the loop that just maps every point to the identity of the group. Nothing moves. So what is the neighborhood of that? What are the infinitesimal deformations of that? Well, because you're sitting at the identity of the group, the infinitesimal transformations in the group lie in the Lie algebra. So an infinitesimal loop group element is a map, well, let's call it F epsilon of theta, that will not go to an element in the Lie algebra near the identity of the group, but it can depend now on theta any way you like. So it will have an expansion of the form a and n, Ta times e to the I n theta. Right? If theta goes from 0 to 2 pi, that'll be a periodic element. I mean, this must be a periodic function. It's an honestly well-defined function from the circle to the group. So if I write it in terms of theta, it must be 2 pi periodic. And the most general infinitesimal element in the neighborhood of the identity is something that lives in the Lie algebra and has non-trivial Fourier components such that it's not just constant in the Lie algebra. It's constant in the Lie algebra, but it's also allowed to vary with theta. And it can either vary like e to the I theta, or e to the 2I theta, or e to the 3I theta, or e to the minus I theta, or it can be a constant. So therefore, what you see is you get generators. The infinitesimal generators are labeled by an element that labels the Lie algebra of the group, and an integer that labels the Fourier component. And that's exactly what these guys are labeled by, right? So A is the Lie algebra direction, and M is the Fourier mode. So these guys tell you which infinitesimal loop group element near the identity you're looking at. You're looking at the element that, as a function of theta, behaves like e to the I n theta, and is in the direction of Ta as regards the Lie algebra of the group. And it's pretty clear that these are all the infinitesimal generators of this loop group. And then, because it's a Lie algebra, you know there has to have a Lie bracket. And when you work out a Lie bracket, lo and behold, that's the Lie bracket you find. So obviously, without the central extension, that's the Lie algebra of the loop group. So what this describes are the Lie algebra of maps from the circle to the group. That's the meaning of what the affine Kac-Moody algebra is. I mean, this is it's maybe not, but you should have seen this. In particular, you see, as a consequence of that, you know there is a natural action of the Virasoro algebra on that. Because you see, the Virasoro algebra is sort of the conformal transformations, and you can think of this as transformations of theta. So therefore, because these are elements, maps from the circle into the group, will be a semi-direct product of the Virasoro algebra and the affine Kac-Moody algebra, where the Virasoro algebra generators act on the theta bit, but don't touch the A bit. And in fact, that's what you find. You see, when you calculate the commutator of Ln with these generators, what you find, and this is again a relatively elementary computation of the kind I have now shown you too many of. Remember, we have the LMs of this fermion system. These are the sums of the different LMs. And if you calculate this, what you find is that this is equal to minus n times j m plus n. And that's just telling you that the Virasoro algebra sort of acts on the theta parameter by a conformal transformation of the theta parameter. You think of it now as acting on the parameters on the circle. And therefore, the algebra you really get in this context is what you would think of as being a semi-direct product of the Virasoro algebra and the Affine-Kac-Moody algebra. The Affine-Kac-Moody algebra does its own thing. The Virasoro algebra does its own thing, but they don't commute with one another, but rather Virasoro times Affine-Kac-Moody gives you Affine-Kac-Moody, namely via this expression. So this is what this system, this innocent-looking system of just n free fermions actually has a lot of structure, because it doesn't just have this Virasoro symmetry, it has actually a lot of structure, and it exhibits in particular this Affine-Kac-Moody symmetry, and that will play an important role later on. Obviously here, this is a free field realization of this Affine-Kac-Moody symmetry, so this k parameter will take very special values. Well, I've written down the values here, but as it turns out, they will be relatively special, and the central charges will be n over 2, where n is an integer, so this is all very special. But you see, once you've written down this algebra, once you write down this algebra, you can also think about finding representations. So, I mean, the algebra altogether in its glory is this. And then I have for Lm with Ln, I mean, this is just an algebra that makes sense essentially for any value of k and c, right? So obviously so we've done so far is we've made it out of free fields. Then this c is a half integer, and this k will be very simple numbers. It will be there'll be integers, but there'll be very specific integers. There won't be just your random integer. But you can guess that somehow there will be also a conformal field theory where this k will not be one of the integers you can get that way, and where this c will not be a half integer. And that will be true, and this will be interacting conformal field theories. They fall into the same sort of family. And what I've produced for you is sort of the simplest incarnation of that you can make out of free fields, but these ideas will generalize to much more interesting examples that will not be free fields. So this is sort of the spirit in which we are working here. We are starting with simple examples, we are discovering structure, and once we've discovered the structure, we'll be able to generalize it to examples that are not just free fields and much more rich in their structure. Okay, I think I probably wanted to write down, not sure whether I wanted to write down anything more. Yes?
What happens if you have n free scalars? Can you construct this consequently arbitrary?
That's very good. So there is actually a construction for the, so if you have, for a simply laced Lie algebra of rank R, if R free scalars, you can produce this Affine-Kac-Moody algebra with this parameter taking the value 1. That will give you, that's the Frankel-Katzikl free field construction of the Affine-Kac-Moody algebra. The canonical construction here is that you take the fermions to sit in the adjoint representation of the Lie algebra, then this parameter will turn out to be the dual Coxeter number of the Lie algebra, which is the value of the Casimir in the adjoint representation. And C will, in that case, always be the dimension of the Lie algebra divided by 2. These are the two canonical free field realizations. And then there is this realization which is called the quark construction, which you can do for any representation M. So then that's obviously more general. But yeah, so in some sense, I may be giving here the wrong impression. So these are the special constructions. So there are isolated versions of this that have free field realization. But if you close your eyes and you pick some random number k and some random number c, it will not have a free field realization. So most of these things will not be free theories. There are isolated examples, and in order to motivate the structure, I started with the isolated examples, and we're going to generalize it to much richer families where they are not realized by free fields. But there are free field realization in terms of bosons, and there are free field realization in terms of fermions. And here I've started with the free fermionic one because that's much simpler. The construction of the free boson is much more complicated because the the rank, the Cartan generators are basically the free bosons as they come out of the box, but the roots of the Lie algebra are exponentials in them, and that's a more complicated construction. I mean, I can, if you're interested, I can explain this, but this is not the easiest construction at this moment in time. Are there any other questions? Yes?
Is this extension of the algebra global symmetry of the theory of free fermions, or?
Well, so the global symmetry are really just the zero modes. So by global symmetry, so the analog of the Möbius group, it would be just the zero modes. So it would just be the Lie algebra itself. So by global symmetry, and I'll come to explain this later, you see the global symmetry are the generators that annihilate the vacuum. And the generators that annihilate the vacuum, you will see, are just the Virasoro generators with m equal to 0 plus and minus 1, and they will be the affine Kac-Moody generators with m equal to 0. So these are the global symmetries, and they just give you a G global symmetry. The other generators will not annihilate the vacuum, and therefore they don't give rise to what you would call a global symmetry. But they constrain the theory, but they constrain it in a more complicated way. They will constrain it by constraining the correlation functions by something like ward identities rather than globals. But I'll come to explain. This will play an important role later. But if you use the word global, it's just G. That was a...
Yeah, so the free boson constructions that you mentioned, are they the bosonized version of these constructions? When you bosonize this particular?
No, that is not... Yeah, so you have to be a bit careful. I mean, not all fermion. I mean, bosonization and fermionization are tricky things. You need bosons at a specific radius to reproduce. So, in general, you can't write this in terms of bosons. But so it's certainly not that. I mean, this is more general because here you basically have a representation free, whereas the Frankel-Katzigel construction really only gives you level 1, and for the simply laced case. In a non-simply laced case, it's even more complicated. There is a free field realization for the level 1 algebra for the non-simply laced case, but it involves bosons and fermions. But I'm getting deep into the weeds here, so maybe I'll save this for some later time. Yes?
Can you still write the Kac-Moody algebra if you gauge the symmetry group?
What do you mean by gauge the symmetry group?
Gauge if the symmetry group is not global, I take, if not for a free fermion, I take a gauge theory.
Well, that will also break then the affine Kac-Moody symmetry. So, I mean, there's something like the coset construction, which that's something I aim to talk about, that you can think of as in some sense gauging the affine Kac-Moody algebra. So what you there do is you have the big affine Kac-Moody algebra, and you look at some subalgebra, and you're de facto gauging the subalgebra, and the question is, what's the conformal field theory that is described by gauging this subalgebra? And that leads to these coset conformal field theories, which I can describe. Any other questions? Okay, so I think we probably have done enough calculations of this kind, right? So it's losing a little bit the novelty value. So let's do something slightly different. So the other thing we'll need to understand before we can get a general description of what a conformal field theory looks like is what the amplitudes, the vacuum expectation values of these conformal fields look like. And I just want to work out a few of them so you get a sense of what they look like, because that will sort of inform us about what we would expect for a general conformal field theory, how we can describe it. So let's try to calculate correlation functions. And I'll start with this example. I mean, we go back to the free boson theory, so we get a sense of what these correlation functions actually look like. So the question we want to ask is, what does d phi of z, d phi of w vacuum expectation value, what is this equal to? I mean, you see, a conformal field theory is not just a set of operators and a Fock space. You also have to be able to calculate vacuum expectation value. I mean, that's what you learn in quantum field theory. Now, in quantum field theory, what you would normally do is you would write down Feynman rules. Now, obviously, here the Feynman rules are a little bit trivial, because it's a free theory, so in this case I can easily work it out. The general spirit of conformal field theory is that it's a quantum field theory that you're going to solve by techniques that are not Feynman rules. We shall virtually never use Feynman rules, because the idea of conformal field theory is that the symmetries are so gigantic that the answer is more or less fixed purely based on symmetry alone. So you're not going to go through the laborious task of working out Feynman rules. You do rather the opposite. You write down the answer. And because the answer is basically unique, well, there are a few parameters, and then you just fix the few parameters by self-consistency. So it's a very different mindset to normally solving a quantum field theory. You're not going to build up the correlators by adding together all the Feynman diagrams. You're just trying to constrain the answer sufficiently much that it's basically unique or fixed up to very little, and then you just fix what remains to be fixed by self-consistency. Now here, I'm going to do it slightly differently because we are in the process of getting a sense of what conformal field theory is. So this one I'll honestly calculate for you, but we'll stop doing that pretty soon. So this is just as a way, you should be convinced that I could also do it that way, and you should in particular be convinced that you don't want to do it that way for more complicated examples. So this is again another one of the strong man, don't need group theory type calculus, but it won't be so bad. So remember that these fields have a mode expansion of the form right? This is the mode expansion of this field as I'd written down there. And now we want to, and remember the Fock space is characterized that an on the Fock space is equal to 0 if n is greater or equal than 0. So here, you see, here is really a vacuum sitting. So therefore, when we put in the d phi on the right, we should only put in the modes that, the negative modes. But then we also have an out vacuum here. And this is sort of the conjugate state. And the conjugation will map an to a minus n. So the conjugate statement to that will be the statement that this is equal to 0 if n is less or equal than 0. So therefore, when we calculate this correlator, we can just plug in the mode expansions for the two fields. Let's call them m and n. So we're going to have z to the minus m minus 1, z to, well, w to the minus n minus 1, and then we are going to have am, an, 0, right? I mean, I've just plugged in for this guy, this mode expansion, these are the n's. And for this guy, the mode expansion, these are the m's. But because of this property, you see the n's should be less than 0, because otherwise an kills the in vacuum, and m should be bigger than 0, because otherwise it kills the out vacuum. Now, this is obviously something we can easily do. Even I can do it on a Friday morning in front of you of a blackboard, because you see, the m's are positive. So the m's are positive, so therefore they are going to kill this in vacuum. So therefore I can replace this product by the commutator. And then what is this commutator? Well, this commutator is just m times delta m comma minus n. So therefore, out of this double sum, only a single sum survives. And now I'm going to write this simple sum a little bit nicely. So I write this as the sum from m is equal to 1 to infinity. I have a factor of m. And then I have w over z to the m. Right? N minus n is equal to m. So I have a w to the m, a z to the minus m. I have a 1 over zw outside. This is the minus 1 and the minus 1. So this is the z to the minus m, the z to w to the minus n is the w to the plus m. So this is what I have to calculate. I've assumed that the vacuum is normalized so that the in vacuum times the out vacuum is equal to 1. Okay, so this I can also write as a sum from 0 to infinity, because for m equal to 0, this term isn't there. And then you know what this is, right? Because this is just 1 over zw. And then this is u d by du of the sum from m is equal to 0 to infinity of u to the m where U is to be set to be W over Z at the end of the day. Right? Because when I take this sum and I take the derivative with respect to U, I bring down a power from M, U to the M minus 1, the U makes this back to U to the M. So this is exactly this sum if I evaluate it for U equals to W over Z. Okay. Now this sum we can obviously do because this is just a geometric series. So therefore, this is equal to 1 over ZW times U d by du of 1 over 1 minus U, where I said U is equal to W over Z after I've done with all of that. Right? Because sum over M to infinity U to the M is 1 over 1 minus U. It's a geometric series. So what is this? Okay, so this is, I take the derivative, this becomes 1 minus U squared, right? And then I have a factor of U in the numerator. So if I plug this in, this is 1 over ZW, then the numerator gives me W over Z, and then in the denominator I have 1 minus W over Z squared. Right? And now you see that, so W obviously cancels. I have a Z squared. I can move the Z squared into the square. And therefore, this is just 1 over Z minus W squared. So that's the form of the two-point function of the free boson with itself. Okay, that wasn't too bad. Now, obviously, now think about doing this for 4 points. Well, okay, so now you probably see that I don't want to do it because then I have 4 A's. Then when I commute them through, I get all the big contractions, blah, 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 and so on. But actually, for the fourth, I mean, in fact, you can write down a general formula. The general formula will look like, so by the same token, except it gets more and more tedious. But first of all, what you observe is that you need an even number of fields, because you see each A has to have another A to be eaten by. It's only 2 A's that have a commutator to give you a number, and if you have an odd number, then after you've taken as many commutators you've left can do, there's 1 A left standing, the last A standing, and the last A standing is either going to annihilate this guy, or it's going to annihilate this guy, or it's going to annihilate both. But it's going to annihilate, so it's going to be 0. So all these correlation functions will be 0 unless there's an even number of these d5 fields. And if there's an even number of them, so the correlation function that is of the form d phi z1 up to d phi z2n, so I assume already that's an even number. And then the answer is 1 over n factorial times 2 to the n times the sum over all permutations rho in S2n in the permutation group with the 2n symbols. The product of I is equal to 1 to n, 1 over z of a rho of 2i minus 1 minus z of rho of 2i squared. I mean, this is a fancy way of saying you basically get all the pairs of fields. I mean, this is the sum over all the possible big contraction. So the big contraction picks any 2 and connects them and replaces them by the propagator, which is just that. I mean, de facto, I've just calculated the propagator here. And the Feynman rule would tell you if I have 2n of those, then I get the sum over all combinations where I contract them pairwise. And for each pair, I get a term of the form 1 over zi minus zj all squared. Now, when I sum over all the 2n permutations, I'm picking up all the possible terms, but I'm picking up the possible terms with a large multiplicity, so I have to divide by the amount, by the number which I pick them up, and the number is just n factorial times 2 to the n, because they're n factorial pairs, and then I have signs which way round I pick them, so they're 1 over n factorial 2 to the n. So these are the correlation functions for the free boson theory. So this is the answer if there's an even number of boson fields, and if there's an odd number of boson fields, the answer is 0. Is that clear, or is this unreadable? Vaguely unreadable, but I mean, you know what it is, right? I mean, it's just the sum over all the pairs. It's not rocket science. Okay, so this is example number 1. Okay, so we see what these sort of correlation functions look like, and sort of the punchline that you should sort of take away from them is there are meromorphic functions in the Zs. They have poles of finite order, but they are global. Well, okay, so I should come clean here. So I made one assumption here. You see, so in this calculation, I assumed that this is a geometric series. So in order for this to be a geometric series, I have to assume that the modulus of W is less than the modulus of Z. So what I implicitly assumed here is that the modulus of W was less than the modulus of Z, because otherwise this geometric series doesn't converge. Okay, so let's assume the modulus of W is less than the modulus of Z, and you calculate the answer. But now you've calculated the answer doesn't care anymore whether the modulus of W is less than the modulus of Z. So then you say, okay, the answer is simply defined by analytic continuation for all values of W and Z, and it doesn't really matter whether it's smaller or bigger. It's just this is in that regime I can evaluate it, and because these fields are boson fields, they should commute. I can always bring them into the order. Also notice that this correlator is independent of the order in which I write down the fields if I define it in that fashion. It doesn't matter whether Z is to the left and W is to the right, or vice versa. So this is symmetric under the exchange of all the fields, and it's globally defined, although when I wrote it down in terms of this mode, I had to assume a certain regime of convergence in order to actually derive it. But then I can extend it by analytic continuation. That will be also the spirit of what we are going to do in the following. Okay, so the next correlator we want to look at is the correlator of the L's. So the next example, let's look at the correlator of the L's. So what about 0 L of Z1, L of Zn? Well, there we can do basically the same thing, right? L of Z is the sum over n in Z, L n Z to the minus n minus 2. So you just plug this in, then you have a sequence of L's. Then you know the in vacuum, you see the in vacuum is annihilated by these if n is greater or equal than -1, because you see L minus 1, remember, is the translation generator, and the vacuum is translation invariant, which we also saw. Remember, this L minus 1 is bilinears in the A's, and when it's bilinears in the A's, if the -1 mode, you will have either a positive mode or 0 and -1, but the 0 mode also kills the in vacuum. So this gets killed for n greater or equal than -1, and correspondingly the out vacuum gets killed for n less or equal than +1. So then you write down in terms of modes, and then you bounce them around, and in principle you can calculate it. Although here you are probably already don't want to do it anymore, because it's going to look a little bit tedious. Well, let's work out a case of a 2-point function. That's the last one I'm going to work out for you, and then I'm going to give up because it's going to get too complicated. Okay, so what would this look like if I do this for the Z and W? Okay, so what do I get? I plug in the sum over n and m. So I have a sum over n and m, and then I have a 0, then I have Ln, Lm, and then I have a Z to the minus n minus 2 and W to the minus m minus 2. Now again, so without loss of generality, m must be less than, so m must be less or less than -1, must be less than greater than less or equal than -2, and n has to be greater or equal than 2, because otherwise it's so therefore this mode will kill the in vacuum because this is a positive mode, so I can replace this by the commutator. Now the commutator I can work out. What's the commutator? The commutator is n minus m times Ln plus m plus c over 12 n squared minus 1 delta m comma minus n. Okay, so the term where I produce a single L, That's not going to make me happy, because this n plus m is either positive or negative or 0. If it's positive, it kills this guy. If it's negative, it kills this guy. If it's 0, it kills both of them. So this term will obviously not contribute in the discorrelator. The only term that contributes is this guy over there. And therefore, what this correlator will be equal to So what is this correlator going to be equal to? Okay, it's good that m and minus n. So if I write this in terms of n, this will be the sum over n greater or equal than 2. And then it will be proportional to c over 12 times n squared minus 1 times w over z to the power n, right? Minus m is equal to plus m, so I get a w to the plus n, z to the minus n, and then I have to divide this by 1 over zw squared, right? These are the minus 2's that I get from the from these terms. Okay, so maybe I don't really want to write it like that. Let me write it as c over 12 times n plus 1 times n minus 1. Okay, so what does this look like? Well, this looks like, okay, there's a c over 12, then I have a 1 over zw squared. And now this looks like, you see, this wants to start out with w over z to the n plus 1. And then I take 1 derivative, 2 derivatives, 3 derivatives, right? So it will take, it look like the sum over u to the n plus 1, and then I take the derivative with respect to u, that gives me the factor of n plus 1, then I take another derivative with respect to u, that gives me a factor of m, then I take yet another derivative with respect to u, so this gives me the third derivative with respect to u of this expression, then this would have become u to the n minus 2, so I'll better multiply in a u squared to bring it back up to this. And then I just evaluate this at u is equal to w over z. And this sum, you see, originally starts at n equals to 2, but I could have started it at n equals to 1. I could have started it at n equal to 0. In fact, I could have started it at n equals to minus 1, because these factors guarantee that none of these terms is 0. So this sum really, well, it doesn't matter. You see, if you take 3 derivatives, the first 2 terms are for free. So you may as well think of this as going from 0, well, now you can write it like this. You just write it as a sum from 0 to infinity, because it doesn't really matter. I mean, the first term that survives is the one that goes like u cubed, because that's the right, and then the u cubed, when you have taken 3 derivatives and multiplied with u squared, this is that. Now you can see again, this is 1 over 1 minus u by the same token. And now I have to take 3 derivatives, so now I'm going to probably make a mess of it, but let's try anyway. So if I take, okay, so the first derivative, let's take it 1 derivative at a time. If I take the first derivative, I get a 1 over 1 minus u squared, as we had before. Then I take the second derivative. Then I get a factor of 2, and I get the third power. And then I take the third derivative. Then I get a factor of 6 and the fourth power, right? This is what I get. So then the factor of 6 times c over 12 gives me a c over 2. Right, the 6 cancels this 12 to give me c over 2. And then I have to multiply this with u squared. So what I'm going to get is w over z squared divided by w z squared. And then it's 1 minus w over z to the power 4. Have I done something bad? Or? Okay. And now you see where this is going, right? So the w's cancel. And I have a 1 over z to the 4, which I can bring inside the bracket. So this is going to be equal to c over 2 divided by z minus w to the 4th power, which is the 2-point function of the stress energy tensor. Is that clear? And now you can see you could do this for 3-point functions. Now, there's one structural thing you can see. You see, so you can commute the L's to your heart's delight. But at the end of the day, all the L's have to be gone. I mean, once you've done all the contractions, the L's will have to be gone. Because there is no, if there's a single L surviving, it'll either kill to the right or to the left. So the last commutator you'll pick will be the C number term. Right? So you have to pick the C number term in the last step, otherwise you're going to get 0. And therefore this correlator will be necessarily proportional to the central charge. There's no way avoiding it, because after doing as many commutators as you want, the last commutator you take, you must pick the C number term, i.e. the correlator will be proportional to C. Now later on, I'm actually going to write down for you a closed form. There's a very neat closed formula for the correlation functions of arbitrarily many stress energy tensors, which you can write in graphical notation. It'll be the sums over all loops weighted with powers of C and so on. I'll explain that to you later on. But this is sort of the first example. And what we see here is that all these correlators will be proportional to C, to the central charge. And there'll be, and this is another example of a correlator that is, it's a meromorphic function in the Z's. Again, what I've done here is I've assumed for this to work, I have to assume that W is in modulus less than Z, so that the geometric series converges. But once I've written down the answer, it makes sense generically, so I define it by analytic continuation. Again, it's independent of the order in which the L's stand there. That's simply the correlation as it's defined. And that's sort of what you find for all of these conformal field theories, these correlation functions of these chiral fields, they'll all be meromorphic functions of the variables. They'll be independent of the order in which they appear. They have poles of finite order, but they're very, very well-behaved, benign analytic functions. Well, they're not quite analytic because they have poles, so they are meromorphic. So meromorphic means analytic, except you can have poles of finite order somewhere in the complex plane. That's exactly what these correlation functions all look like. And so now you have a sort of sense of what these sort of benign example, the simple examples of conformal field theories look like. And now I'm going to postulate for you the sort of properties a generic conformal field theory has. And what you want to do is we want to understand the correlators and the operators of a conformal field theory. And you see, for example, for the free boson theory, remember, this is the field operator, and these are the modes of the field operator, and this generates a Fock space. And the Fock space is generated by the terms of the form. And what you should think of, and I'll explain that to you in more detail, this is the operator that corresponds to the state A minus 1 on the vacuum. It corresponds to one specific element in this Fock space. And what we want to do is we want to be able to write down field operators not just to that state, but to all states of our Fock space. Because you see, every state of the Fock space, there should be a corresponding vertex operator that creates this state from the vacuum. And we should be able to calculate correlation functions, not just for these sort of simple generating fields, but for all of them. So what I want to explain to you is sort of a framework in which you can define the operators associated to all the states of the theory, not just to the simple states of the theory. And we want to understand the structure which the operators of all the states of the theory form. Now, this is what's called in the mathematical literature a vertex operator algebra. So we're going to define for you is a vertex operator algebra where you're not just having the vertex operators or the field operators associated to sort of what you may think of as being the generating states, but the field operators associated to any state of your Fock space of the theory, because you should be able to produce any state in the Fock space and insert it into your correlation function, so you should be able to define vertex operators associated to any of these states. So this is what we aim for, and the idea is, and this is what I'm sort of beginning to hint at here, is that there is a field state correspondence. So what we want to postulate is, and then I'll explain to you how we can characterize this abstractly and what we can read off from it, and then I'll show to you that the examples from which we started fit exactly into this framework, but it describes this in a more general setting and in a setting that will work in all sorts of contexts. So the idea is that there's a field state correspondence Yes.
It's not clear to me why this operator corresponds to this particular state.
Yes, I agree with that, but you'll see it in a second. So what is this field state correspondence? The idea is that for any state in the Fock space, let's call it phi, is an element of the Fock space of your theory. Now, for the moment, this is, you may think of this as being this free boson, but that will be true for any conformal field theory. There should be a vertex operator, which we call V phi of z. And V phi of z should have the following property. It should produce V phi of z, when you apply it to the vacuum, should give for you e to the z L minus 1 times the state phi. Or put differently, if you take the vertex operator and you evaluate it at z equal to 0 and you apply it to the vacuum, then it should give you the state phi. So the vertex operator is the operator that produces the state phi if you insert it at the origin. Now, if you don't insert it at the origin, then it's obviously related by a translation relative to the vertex operator that's inserted at the origin. And the translation operator is e to the z L minus 1, because remember, L minus 1 is the Möbius transformation that corresponds to z goes to z plus epsilon. So the operator e to the z L minus 1 is the translation operator. The operator e to the z L minus 1 has the property that so e to the z L minus 1, a vertex operator phi at u, e to the minus z L minus 1, is just going to give you the vertex operator at u plus z. Right? Because it's the translation operator. It's L minus 1 is the infinitesimal translation generator. So e to the z L minus 1 is the translation by the amount z. So therefore, if I take any vertex operator and I conjugate it by the translation, I basically shift everything by z. So this gives me the vertex operator evaluated at u plus z. So in particular, you see, having that, if I apply this e to the z L minus 1, v of phi and 0, e to the minus z L minus 1 acting on the vacuum, you see e to the L minus 1 annihilates the vacuum. So therefore, this will be equal to the vacuum. Then v of phi of 0 on the vacuum gives you phi, and therefore this is equal to e to the z L minus 1 acting on phi. And this is exactly, on the other hand, v of phi of z on the vacuum. So you see this implies this, together with the fact that the vacuum is translation invariant, and e to the z L minus 1 is the translation operator. Is that clear? So I'm making a little bit of a jump here. So this is a crucial moment. So make sure you ask if you are confused, because we are going to sort of now take a turn and we are going to run in a certain direction. And this will be the first step, and everything will hinge on what we are doing in the next 10 minutes. Okay, so what I'm saying is I'm postulating that for every state in the Fock space, there's a vertex operator. The vertex operator at 0 on the vacuum gives me the state. That's what you call the field-state correspondence. 0 is the place where the state space is identified with the vertex operators. And I can move vertex operators around by e to the z L minus 1. L minus 1 is the translation operator. So e to the z L minus 1 should transform the vertex operators in that fashion. And then this relation follows. Okay? Now I was asked, I said that this is the vertex operator corresponding to the state A minus 1. But now we can answer that question, right? Because if you give me a vertex operator, I will find out what the state is by taking this vertex operator and applying it to the vacuum at 0. So let's just take this vertex operator and apply it to the vacuum at 0, right? Okay, so what is d phi applied to the vacuum? Okay, so d phi of 0 applied to the vacuum. Okay, let's first write d phi of z applied to the vacuum, because there are negative powers there, so I'm a bit scared. So this is sum over n, z to the minus n minus 1, an applied to the 0. So remember, an applied to the 0 is 0 unless n is, so the positive mode's annihilated, the 0 mode annihilates it, so n is less or equal than minus 1. That, you see, makes now a lot of sense, because that means that this doesn't have a pole when it applies it to the vacuum, right? The only terms that survive are such that the exponent here is 0 or bigger. And now if you take the limit z goes to 0, well, then obviously only the term survives where the exponent is equal to 0. All the other terms die when you take z goes to 0. So what's the exponent for which the exponent is 0? That's the mode n is equal to minus 1. All the other ones come with positive powers of z. So this is therefore equal to a minus 1 on the vacuum. So that's the reason why I claimed this is the vertex operator corresponding to that state. It's simply the statement that if I take this vertex operator, apply it to the vacuum, and take z to 0, the state I get is the state I identify to be associated to that vertex operator. That's the definition of it. And if I apply this definition to that field, I learn that the corresponding state is that. But obviously you can do this, so now the idea is that you don't just have a vertex operator associated to a minus 1, but for any state you'll have a vertex operator, and the vertex operator will be the identification of which vertex operator corresponds to which state is given by the equation in the box. It tells you what's the identity. If you give me a vertex operator, I know which state you are talking about by applying it to the vacuum and taking z to 0. That's my identification of what this vertex operator is. Now, the idea of this characterization is that, you see, what we've seen in all of these correlation functions is that these vertex operators all commute with one another, at least in the bosonic world. And in the following, I shall, I think, probably exclusively talk about the boson. If you're interested, I can also talk about superconformal field theories, but the structure is simpler if I just talk about the bosonic theories. You see, these correlation functions, it didn't matter in which order these field operators stand. So what we would like to believe is that these vertex operators are all mutually local. And what this should mean is that V of phi and z and V of psi and zeta is equal to V of psi and zeta, V of phi of z. That's what we're going to call locality. And we've seen this in the correlation function. In the correlation function, it didn't matter in which order they appeared. So they're local in this sense, yes. Well, so what I said, for the convergence of the series, I assumed that one was to the left of the other. So, but then after I calculated it, the function was defined. I could define it by analytic continuation, and the analytically continued function was independent of the order in which the vertex operators appeared. It just depended on 1 over z minus w squared, and it's the same whether it's z minus w or w minus z. It's the same function. So I assume that the vertex operators are all local, and this is motivated by the examples I've showed to you. All the correlation functions had this property. So what I'm postulating is that the vertex operators of a conformal field series are characterized by these two properties. They'll be local in this sense. So this is true if zeta is not equal to z. Obviously, if they're equal, then there'll be poles that we've seen. But if zeta is not equal to z, they'll be local. And then I say that v of phi of z is characterized by the property, by the defining property, that it acts like that. And now, the beauty or the simplicity of this approach is that a vertex operator is uniquely characterized by this property. So this, I now claim that this property characterizes v of phi of z uniquely. You see, you could have been worried about me saying there's a vertex operator associated to each state, because what I told you is, if you give me a vertex operator, I can tell you which state it's associated to. But how may it not happen that there are two different vertex operators and they would correspond to the same state? So which one would be the vertex operator associated to the state? So I have to show that this characterization is unique. Otherwise, I've sort of obviously done something somewhat illegal, because I've labeled vertex operators by something that wouldn't characterize them uniquely. And the observation is that locality basically tells you that that is the case. And it's sort of, in some sense, embarrassingly obvious. So suppose I have another operator. So suppose w of z also has the property that I have evaluated it on 0, it's equal to e to the z l minus 1 on phi, and it's also local. Then you see w of z acting on any collection of phi 1, zeta 1, up to phi n, zeta n on the vacuum. You see, it's the same because of locality. I can move w to stand directly in front of the vacuum. So this is equal to v of phi 1, zeta 1, up to v of phi n, zeta n, w of z on the vacuum by locality. But then w of z on the vacuum will be the same as v of phi of z on the vacuum, because I assume that w of phi of z on the vacuum does that, and I know that v of phi of z on the vacuum does the same. So on the vacuum, they're doing the same thing. But v of phi of z is also local with respect to these guys. So this is therefore equal to v of phi of z applied to v of phi 1 of zeta 1, v of phi n of zeta n on the vacuum. So therefore, the action of w doesn't just agree on the vacuum with the action with the vertex operator phi of z, but it agrees on it on any element that I can make by applying as many vertex operators as I like on the vacuum. I can take contour integrals, I can produce modes, I can do all of it. So that tells you that on the Fock space, these two vertex operators agree, and the Fock space is dense in everything, so therefore these vertex operators agree. So therefore that tells you this property, together with locality, characterizes vertex operators uniquely. Because if they do the same thing on the vacuum and they're local, then they do the same thing on everything. Because you can commute it through on the vacuum, they do the same thing, and you commute it back, and therefore they do the same thing on everything. So this tells you that this is a very elegant way of characterizing vertex operators, as long as they're local, and all our examples are local, and all the examples I'll be dealing with will be local. I can characterize vertex operators simply by saying what they do on the vacuum. And that will turn out to have very profound consequences for allowing us to describe the structure of conformal field theory in a sort of a very, very elegant form. Okay, is that clear? So this is sort of key. So this is what I'll be using over and over again. And I'll use this property to derive all sorts of neat facts about conformal field theories. And this innocent sounding formula and assumption is extraordinarily powerful. It allows you to derive, for example, the Virasoro algebra almost as a two-liner. And I'll explain to you later on how the Virasoro algebra comes out of this. It allows you to calculate the commutators, not just of the simple fields, but of the modes of any fields with one another in closed form. That all comes out of this formula in a way I'll explain to you shortly. Okay. Okay, so before we continue, let's derive a few simple consequences. So there's one simple consequence which comes out of this property. So let's take this to be, well, actually we can take this to be u, doesn't matter. So suppose we take the derivative with respect to z, and then z equal to 0 of both sides. Let's take the first derivative with respect to z, and then take z equal to 0. When we take the first derivative with respect to z, then what you find is that this is the first derivative of this. What is this? Well, I mean, the first derivative means you take the terms that are linear in z. The terms that are linear in z is an L minus 1 standing here, and a minus L1 standing here. So what this is the commutator of L minus 1 with this vertex operator. So this is just the commutator of L minus 1 with the vertex operator.